Suppose we draw an unequal probability sample. In this example, we're estimating the proportion of people in our class who prefer to sit in the front of the classroom. We want to estimate something about the proportion among those who are actually sitting in the front of the room. So we drew an unequal probability sample. We drew 50% of the people sitting in the first 3 rows and only 10% of the people sitting in the back of the room. Now suppose we wanted to go back to our original question. What's the preference among the entire class as a whole? If we simply analyze these data naively, we might take the mean of those who responded, see what proportion of the sample prefers the front of the room, and assume that that's the same as the proportion of the whole class who prefers the front of the room. But if we do that, we run into a problem. Our sample overrepresents people in the front of the room, so it might give us a wrong answer on average. We're now going to talk about sampling weights as a strategy to resolve this problem. Sampling weights take us from an unequal probability sample and get us back to a population level estimate. So let's think about those sitting in the back of the room. These people were sampled whenever their random number was less than 0.1. So on average, 1 in 10 of these people responded. Each of them who responded thus represents about 10 people. We're going to call that their sampling weight. It's 10, which is 1 divided by their probability of sample inclusion. They each had a 0.1 probability of inclusion. They represent 1 over 0.1 equals 10 people. Now let's turn to the people in the front of the room. They responded if their random number was less than 0.5. This means that on average, 1 in every 2 people in the front of the room answered the question. Each of those people represents 2 people, not 10. For them, the sampling weight is 1 divided by the probability of sample inclusion. That's 1 over 0.5, which is 2. Armed with sampling weights, we can move from the unweighted estimator of the mean to a weighted estimator of the mean. So let me start by talking about the unweighted estimator in math. The unweighted estimator says let's take a sum over all individuals I in the sample. So like I equals 1, I equals 2, I equals 3 might all be people in our sample. We're going to take the total of their preferences for sitting in, say, the front of the room. How many people in the sample preferred the front of the room? Then divide by the number of people in the sample. If our sample was a simple random sample, this would be the way to go. But our sample is not a simple random sample. The people in the front of the room count for 2 people, and the people in the back of the room count for 10 people. Sampling weights let us resolve this problem. So a sampling weighted average will look very similar to the unweighted estimator. We'll take a sum over all the people in our sample. For each person, we have their response, yi, coded, for example, 1 if they prefer the front of the room, 0 if the back of the room. We'll multiply that response by their sampling weight. That's 10 for the people in the back of the room and 2 for the people in the front of the room. Take the sum of the weight times the response and divide by the total sum of the weight. So while we can think of the unweighted estimator as estimating what proportion of the people in the sample prefer the front of the room, we could think of the weighted estimator as saying what proportion of the total weight in the sample prefers the front of the room. What's great about sampling weights is that they let us get back to the population average, even when our sample was drawn with unequal probabilities. It's really good because all we need to know is that probability of sample inclusion. If you know the random number cutoff by which people included themselves in the sample, then you can create a weight for those people. When you know that probability of sample inclusion, you can then take your weighted average and get a population mean estimate, even if your sample was drawn with unequal probabilities.